Okay, thank you, Alicia. Well, we're really pleased today to have Michael Köhl speaking at our JQI seminar. Michael got his undergraduate degree in Heidelberg in 1998, and from there he went to MIT, where he worked with Wolfgang Ketterle for his diploma thesis. In 1999, he went to MPQ in Garching to do his PhD work with Ted Hensch, and then to ETH Zurich for his habilitation with Tilman Esslinger. Then he was recruited by the University of Cambridge, where he quickly rose to become a fellow of Trinity College and achieve the prestigious rank of professor, which is considerably more prestigious in England than it is in the US. And in 2013, he moved to the University of Bonn as a professor of physics. Through all of this, he has produced some of the most important landmark experiments in cold quantum gases, including excitations of superfluids, atom lasers, degenerate Fermi gases, Bose-Fermi mixtures, quantum phase transitions, collisions and molecule formation, not to mention some precision spectroscopy. And today he's going to be telling us about cold atom experiments that realize a Fermi Hubbard model in two interacting layers. Michael, take it away.
Well, thanks a lot, Bill, for the kind introduction, and thanks for having me for this seminar. I think it's important that we keep up these seminars during the times of this pandemic, and it's really great that you run this great seminar series even in these challenging times. So in my talk today, I would like to present you some recent work that we did on ultracold fermionic atoms and optical lattices here at Bonn. And in the title slide, you pretty much see the sketch of what we do, right? We create a periodic potential landscape using interfering laser beams. We load ultracold atoms into this in two spin states, which are here denoted as blue and red balls. And then we look at this with a high resolution microscope. And we look at what are the ground states, what are the different phases, what are the excitations in this model system. And the goal of the research is to investigate strongly correlated quantum matter. What do I mean by this? Well, strongly correlated matter is characterized by an interplay between kinetic energy and interactions, and in our case also dimensionality. And we use this interplay to create new collective phenomena. And this is a field that is traditionally researched in condensed matter physics. And prominent examples are, of course, superconductivity, in particular high TC superconductivity, which emerges in strongly interacting systems. However, in condensed matter, there have been, of course, always the challenges to really get to the microscopic origin of things, because often things are very difficult to observe at the level of the elementary quanta, and also to write down Hamiltonians which accurately reflect the physics that is going on in a real material. And for almost 20 years now, ultracold gases have provided us with a tool to do this very accurately, namely to create very clean and very tunable experimental platforms, for example, using these ultracold atoms in so-called optical lattices, and to study correlated many-body effects. And probably the first example into this direction was the observation of the superfluid to Mott insulator transition in ultracold Bose gases in 2002. And since then, the research has also shifted to the direction of fermionic particles in optical lattices, which are much closer, much more closely resemble the physics of electrons in a solid. So really to emulate the physics of electron gases in solids, we use these ultracold fermionic atoms in these optical lattices. The major challenge that we face in this approach are, of course, and I'm sure you are aware of this, to reach low enough entropy states. right? If you study a conventional solid, say at 1 Kelvin or hundreds of millikelvins of temperature, you're way, way below the Fermi energy. So you're at the 10 to the minus 5 times the Fermi energy approximately. And these are very low entropy states measured with respect to the Fermi energy. With cold gases, we're much hotter than this in this relation. So we're talking about energy scales which are maybe in the percent range of the Fermi energy. And we're currently drive to bring the temperatures and the entropies lower. But currently we're in this range, but I will still show you that we can see interesting effects even there, such as quantum magnetism, which is a particular topic of this talk. And so what we intend to do here is what is often referred to as a quantum simulation or a quantum emulation, which should help us to understand better the properties of solids near their ground states. And the basic concept behind that is illustrated on this transparency. So for example, when you look at the left-hand side here of this transparency, you see the crystal structure of a high temperature superconducting compound, which is a complicated lattice geometry composed of 4 different constituents. And this, of course, is currently at least near to impossible to really mimic with optical lattice arrangements. But theory colleagues have advised us over decades of research that this complicated lattice structure can actually be mapped onto something which is conceptually much simpler, and that is called the Hubbard model. So that is the lattice model which reduces the whole complication of the real lattice structure to a few simple parameters. And essentially what we do is we assume that we can reduce this lattice structure to a square lattice where particles can hop through the lattice. So there is a kinetic energy associated with the quantum tunneling, and there is some interaction energy when 2 particles of opposite spins go to the same lattice side. And if we believe in this approximation or the simplification, then we can really write down a microscopic Hamiltonian, which is shown here. That is the Hubbard Hamiltonian that was invented in the 1950s already. And this looks really simple. However, it is generally not solvable for fermions on a lattice. And now, in order to find out what are the ground states of this Hamiltonian, what are the excitations, what we intend to do is a so-called quantum simulation. So we try to build an analog quantum computer, which basically simulates the physics of precisely this Hamiltonian. And well, that is the goal of the research here, and I will show you how far we get in this endeavor. So let's look at the specific problem of spin 1/2 fermions on a square lattice in 2 dimensions. And there is one specific case for which we know how the phases look like, and that is the case for half filling. So half filling means that we have equally many spin up particles as we have spin down particles, and we have just as many particles in total as we have lattice sides. So on average, 1 particle per side can be spin up or spin down. And now if we have very weak interactions between the particles, then we do have the situation on the left that we have that these particles arrange themselves randomly on the lattice. We have empty lattice sides, singly occupied sides, and doubly occupied sides. So we have a large amount of density fluctuations in the system. And as you can see from all these vacancies that we have around, the system is compressible. So if we would apply an external force, we could increase the density because the particles could fill up the gaps. And that is what we call a metallic state, because this is pretty much how an ordinary metal like copper or so would look if you would look at it on a microscopic level. Now, if we start to increase the repulsive interaction between the particles, then of course the doubly occupied sides, they become energetically disfavored. So this means they become suppressed, and the particles, they fill up all the voids, so that essentially every lattice side in the end is occupied with more or less precisely 1 particle, and thereby getting rid of all the interaction energy. Now, in this state, which is called the Mott insulator, the density fluctuations are suppressed, and the state is incompressible because there are no empty spaces where particles could move to when I apply gentle confinement to the system. So that is a classic form of an insulator that is induced by interactions rather than by filling up the Bloch bands. And this crossover between metal and insulator, that is what happens at relatively high temperatures. However, if we lower now the temperature, something magically happens, namely that we find that there is actually a second order phase transition to an antiferromagnetically ordered state. And that antiferromagnetism arises due to the super exchange interaction in the Hubbard model. Remember, the Hubbard model has no magnetic interactions to start with. It has only a local on-site interaction. But if particles are cooled down to low enough temperatures, then they actually do virtual hopping process to the neighboring site, and they spot where the neighboring site has equal or opposite spin. In an energetically favorable situation where on a neighboring site the spin is in opposite arrangement, and then you have this unique antiferromagnetic ground state for any interaction. So this is basically what we know and has been known since 50 years, that half filling the situation of the Hubbard model looks like that. However, if we go away from half filling, the situation becomes much richer and much less known. In fact, we don't know what the ground state is for arbitrary filling. Here's a sketch which I've taken from a few-year-old review on high-temperature superconductors from Øystein Fischer, and where he tries to sketch basically how he would envisage how the phase diagram looks like if we introduce doping. So if we remove particles from the system, so this whole doping. So for a small amount of doping, the antiferromagnetic persists, but then as we dope more, the antiferromagnetic order will go away, and there are suspicions that there could be a pseudo-gap phase, or there could be even a new superconducting phase appearing, which some people believe could be the origin of the high-temperature superconductivity in the cuprates. But this is still pretty much unknown from a principal theoretical level, and this is what we're trying to get into with this research on the ultracold atoms. Currently, we're basically at the tip of the iceberg here, so we're at the tip of the antiferromagnetic dome in this picture. For us, it's still a little bit of a way to get down to temperatures where we could see potential superconductivity. But yeah, we're trying to get better every day and eventually hope to reach this state. So experimentally, as I showed already in the introduction, our system is composed of the following setup. We do have a setup of several interfering laser beams, which at first creates a stack, pancake-like stack of two-dimensional layers, where we confine the atoms to very thin slices, where they're kinematically really two-dimensional, and then we superimpose a lattice into this on these two-dimensional planes and create a two-dimensional Hubbard model on a square lattice. All of this done is at the center of a high-resolution microscope. We do not have single-site resolution in these pictures. We have a resolution of about 2 or 3 sites, but I will show you later in this presentation that we can actually measure magnetic correlation to the nearest neighboring lattice sites, even without seeing them in real space. We can measure this basically in Fourier space. Okay, and then the typical pictures that we extract from the experiment, they look the following. So I will show you now a series of 3 in-situ pictures for different interaction strengths. And our apparatus is capable of taking always 2 pictures for the very same experimental realization. So this can be either a picture of singly occupied sites and a picture of doubly occupied sites, or this could be a picture of spin-down densities and spin-up densities, for example. So in this picture here, I show you the singles doubles pictures, and you see basically the particles are confined overall in a harmonic trap. So the density is highest at the center. And so this means at the center, we expect to see a higher double occupancy of the particles, and at the edge of the cloud, there will be a single occupancy, just by statistics for small interactions. And that's what you see in these pictures. So you see that the singles density has this ring, has a hole at the center, and the doubles density is very much concentrated at the center. Superimpose these two pictures, you get the total density, and that is the black curve on the right. So where you basically see that the density reflects the overall shape of the trapping potential.
Michael, let me just clarify something to make sure I've understood correctly. You're telling us that you can do the two pictures in what is essentially a non-destructive way. That is, you get both pieces of information on a single sample.
Yes.
Yeah. Okay, good.
So that is important for us in the later part of the talk, because we can, for example, compute the correlation function of spin up minus spin down. And that's why we cannot work with averages, but we really have to take these data on one experimental realization.
Right. Yeah. Thanks.
Okay. Now, if we increase the interaction strength, then what we see is, so now this is now in a ratio of interaction energy to kinetic energy of 8 rather than 2. Then we see that we dramatically reduce the amount of double occupied sites and blow up the region of singly occupied sites, because the particles have to go somewhere. And if we go even further, say to a ratio of 12, then the doubles are gone all the way to 0, and we only have singly occupied lattice sites. And then you see that despite the fact that we're having the underlying harmonic trap, we get a flat density distribution in the center, which reflects the incompressibility of this Mott insulator state. So what you see here is the crossover from the metallic phase to the Mott insulating phase. One is compressible, so the density varies as the trap potential provides external confinement. And in the Mott insulator, we're incompressible, and then the confinement of the trap does not change the density anymore. In other words, this is also for us a way to measure compressibility. So we simply take the derivative of the density with respect to the potential, and this is a direct measure of the compressibility of the trap. All right, so so much for the background. And now in this talk, I would like to show you two different experiments that we conducted over the past year. And the first one is the question of what happens when we go to attractive interactions, and the question of can we use actually attractive interactions to learn anything about the Mott insulator for repulsive interactions. And the second question is what happens when we couple two antiferromagnetically ordered states in a bilayer configuration. So the first question about the symmetry between attractive and repulsive interaction stirs at a very basic property of such fermionic particles and lattices, and that is the particle-hole symmetry. So if you think about the standard textbook example, that you do have a periodic arrangement, you throw in a gas of ideal fermions, then you know there is the band structure of the Bloch band, and the fermions fill up the available quasi-particle states up to the Fermi energy. So basically, when you look at the dispersion relation, which is the blue curve here, and you start to fill it up with fermions, you start from the bottom, and you fill up all the available states until you've exhausted all your particles, and that is the Fermi energy. And that is when you view the whole system from the perspective of filling a vacuum with particles. Now you could do the exact opposite. You could say, okay, what happens if I have a completely filled band and I start removing particles from this? So in this case, you would start from the very top of the band structure and would work your way downwards as you add more and more holes. And then you would get to a Fermi energy, which is sort of Fermi energy of the holes measured with respect to the completely filled band. And as you know, probably from your condensed matter classes, that these two pictures of thinking about the same state in terms of particles or in terms of holes is completely equivalent. So that is there's an exact symmetry between the particles and the holes. Filling vacuum with particles or filling doping a band insulator with holes is the same thing. Now the question is, what happens when we talk about particles with a spin? So what happens to particle-hole symmetry for spin-full particles? And of course, we have to be a little bit more careful when we do that. But there is a proper particle-hole transformation that we can do, which is depicted here on the top left corner. So you see that basically we map the spin-up particle to a spin-up particle, and we map a spin-down particle to a spin-down particle, but with a phase prefactor, which depends on the index of the lattice side. And if you do that, and you do this mapping, then you will find that a spin-up particle maps onto a doubly occupied side, and a spin-down particle maps to a hole, so an empty lattice side. That is shown on the bottom left graph. That is basically what this particle-hole transformation does for a spin-full system. And if you take this analogy now further and ask the question, what happens to my many body states if I do this particle-hole transformation, then you see that this Mott insulator, which is mainly singly occupied sites to start with, so either spin up or spin down, then maps to a state of local pairs. So say every spin up becomes a local pair and every spin down becomes an empty site. So we have an arrangement of local pairs which are randomly distributed. And if I do the same thing for an antiferromagnet, then I actually get a more exciting state. I get a charge density wave state of pairs. So I get an alternating occupation of the lattice with pair, empty, and so on and so forth. So every state there has its particle-hole transformed mirror state. Now, if we do that, we have to be a little bit more careful, actually. If we do this particle-hole transformation properly, we have to check what are the conserved quantities and how do these states map onto each other. And what we then find basically is when we do this transformation, the sign of the interaction flips. So we go from positive to negative U, or from repulsive to attractive. And at the same time, the roles of the chemical potential and the Zeeman field, so the spin imbalance, they also flip. So basically, we can write down our global chemical potential as a spin-independent chemical potential, which tunes the total density, and a Zeeman field. So that is termed in analogy to condensed matter physics, where you have a Zeeman field to lift the degeneracy of the spin populations. Here, of course, with cold atoms, we just fill in more spin states of one or the other kind, but it's still called the Zeeman field. And they basically flip their roles. And that is the prediction for the particle-hole symmetry in a spin-fold system, and this is what we were setting out to measure. And if we do that, so if we believe in this mapping, what you then find is that all of these phases that you know for repulsive interaction, so that's basically the same phase diagram I showed you in the introduction, antiferromagnet here, pseudo-gap, and D-wave superconductor, for a spin-balanced system with repulsion, maps now onto a system where we have attractive interactions, but now we choose as a function, as a tuning parameter, the magnetization rather than the doping. So in other words, the spin imbalance rather than the doping. And we find always the corresponding phases. So the antiferromagnet maps to the charge density wave, the D-wave superconductor would map to the D-wave antiferromagnet, and so on and so forth. This was pointed out for the first time in 2009 by Thierry Jamarki and co-workers. And they pointed at the fact that really you can observe the same phase essentially, either with repulsion or with attractive interactions. So the first thing for us was to just look at the particle-hole symmetry at half filling. That is a very conceptually very simple experiment, and also from the interpretation it's very simple. So when we start out with zero interaction and half filling, so that is the point here at the very center of the plot, then we have 25% singly occupied sites, 25% doubly occupied sites. There's just statistics, there is nothing there. Now, if we increase the interaction to becoming repulsive, of course, we increase the amount of singly occupied sites and we reduce the amount of doubly occupied sites, and then you go to the right of this curve. And eventually, you reach the Mott insulating state where essentially everything is singly occupied and then nothing is doubly occupied. If you go the opposite direction, then of course the reverse happens. So you increase the amount of doubly occupied sites and reduce the amount of singly occupied sites, because now the particles are attracted to one another, and it's much better for them to form local pairs rather than to disperse throughout the lattice. And the exact mirror symmetry of these data, that shows you the particle-hole symmetry for half-filling. But now the question is, can we also see this for doping and for spin imbalance? And so we want basically to interchange the roles of the chemical potential and the Zeeman field while flipping the interactions and still see if the data collapse onto one another. So on the left-hand side, I show you a measurement of the so-called equation of state of the gas. So that basically measures density as a function of chemical potential for attractive interactions and for a spin-balanced gas. So you see the doubly occupied data are the gray data points, and the singly occupied densities are the green data points. But that's for some interaction of -8, I believe. Right, so we have spin balance, we have attractive interactions, and we get the behavior of density versus chemical potential. Now, if we now flip everything, so we now go to repulsive interactions and go to spin imbalance, we have to find out where is the chemical potential of 0. And now it's a bit more complicated to see this here. So these are now the equation of states measured in this direction for spin imbalance. So red data points are spin up singles densities, and blue data points are spin down singles densities. So we subtract the doubles because they don't contribute to the spin imbalance. And on the x-axis here is the Zeeman field. So if the Zeeman field is 0, we have spin balance. And as we increase the Zeeman field, we create a larger and larger spin imbalance between these states. And you see, if we now look at the case of 0 chemical potential, how these two densities, spin up and density, they go apart from one another. And now we want to match this information with the information for the attractively interacting case. And what we see is that this essentially perfectly collapses onto one another if we now plot this, the attractively interacting case as a function of chemical potential, and the repulsively interacting case as a function of the spin imbalance, the Zeeman field. So there are no free parameters here. It's just rescaled everything in tunneling matrix elements, so kinetic energies. And you see the gray data points from the previous transparency, as well as the red and the blue data points for the majority and the minority spins. So we get excellent data collapse, and this really shows that this particle-hole symmetry works, so that we get the same equation of state as a function of density, in one case as a function of chemical potential, and the other case of Zeeman field. And we can take this actually further. We can now go on and compute thermodynamic quantities and find out whether this mapping actually works also for thermodynamic quantities, which it should. For example, we can measure the compressibility. I showed you in the introduction that compressibility is basically the slope of the density versus the external confining potential. And for example, if we look at the red data here, that is repulsive interaction as a function of the chemical potential or density, then we see, okay, so initially the compressibility goes up, and when we reach half filling, so basically that the whole lattice is filled up with particles, with one particle per side, then we get to a minimum of the compressibility. That is precisely the Mott insulating state, where I showed you the pictures of. And that is perfectly expected that you observe this as long as you have still holes in the system. So as long as you're here, compressibility can be higher, but once you reach the half-filled case of the Mott insulator, compressibility goes to a minimum. Now, what would be the equivalent thermodynamic quantity of the compressibility for the attractive interactions? Remember, the repulsive interactions compressibility is density, so it is the question of whether we can actually fill voids or shift the density around. Now, for attractive interactions, the equivalent would be whether we actually are able to split the local pairs. So that is basically spin susceptibility. If we apply a weak magnetic field, whether we are able to split the pairs. And we can measure this. And you see then that the data for the spin susceptibility collapse perfectly onto the compressibility. So we really see that the behavior of the spin susceptibility for attractive interactions and zero chemical potential is exactly the same as the compressibility for repulsive interactions and zero spin imbalance. So this shows that these thermodynamic quantities actually also map extremely well onto each other under this particle-hole transformation. So this means for the future, if we want to detect a certain complex quantum phase, you can basically always choose whether you want to work on the attractive side or on the repulsive side. So in one case, you look for spin signatures in the case of with spin imbalance, or you look for density signatures for the spin balanced case. But the phases, they map precisely to one another, just as Jamarki and co-workers predicted 10 years ago. Okay, so now let me...
Michael?
Yes.
Sorry, this is Alicia. Can I ask a question before you move on?
Sure.
Do you get any improvements in terms of like entropy per particle, doing it different ways? You know, like I guess I was wondering if sort of they suffer from technical problems in slightly different ways.
They
possibly.
do. So this is a question I cannot fully answer because we have optimized our system over 10 years to work really well with repulsive interactions for the cooling and preparation sequences. So that is and then we spent a few months on trying to improve it for attractive interactions, and we ended up at the same parameters in the end.
Okay.
I'm not saying that we cannot get better if we spend another 10 years on the attractive interactions as well, but sort of at first we ended up basically with the same experimental starting conditions for both cases. But I agree with you that this is certainly a hope. So there are two things. So one is the preparation could be better, or the detection could be better, right? For example, if you would like to observe a D-wave superconductor with spatial imaging, that will be hard because that doesn't have a spatial structure just as an antiferromagnet. But it could be much better, for example, to look for it on the repulsive side where it is actually an antiferromagnet. Sorry, on the attractive side where it's actually an antiferromagnet. So from this point of view, we're also looking at this mapping that for some certain phases which may have complicated signatures in one configuration, they could be better detected in the opposite configuration.
Okay, great, thank you.
Okay, so now let's talk about the bilayers. So now I'm extending now the physics from a single two-dimensional sheet of Fermi gases in the square lattice to two layers which are coupled to one another. So experimentally, we do this by superimposing a super lattice in the third direction, which allows us to couple precisely two layers to one another. And in this problem, we now have two different hopping amplitudes. So we now have the hopping amplitude in the plane, and we have the hopping amplitude between the planes. And you could think of this in the following way. So think about it first, that the hopping in the plane is much, much greater than the hopping between the planes. Then we can treat the hopping between the planes just as a perturbation. But we basically will see the fact that we get antiferromagnetic correlations in each of these planes as before. And we then have to find out how much is this perturbation adding or subtracting to these correlations. If you think about the opposite situation, that the hopping between the planes is much, much stronger than the hopping within the planes, then the physics, of course, looks very differently, because then you would expect to observe singlet across these bonds between the planes. And the question then is, what happens to these, what are the transverse correlations of these singlets, if there are any? And so conceptually, these are the two limits. And that is, of course, a case which has been studied a lot theoretically over the last 25 to 30 years. Because it is basically the simplest model which takes you from 2 dimensions to 3 or 2 plus epsilon dimension. So that's the smallest way how to start building up a real solid. And people were interested in what these correlations are. I can tell you straight away, at 0 temperature, you would expect that there is a quantum phase transition between these limits, but of course, in our case, we do not observe a quantum phase transition. We only see crossovers because we're not at 0 temperature. So experimentally, that's how it looks like. So we create now this stack of bilayer systems, which have an adjustable tunnel coupling between them. And on top of this, we use optical potentials to flatten out these potentials. So we work now with homogeneous Hubbard models in this configuration. And these homogeneous regions, they're surrounded by barriers where we split off the low density parts, which creates us then relatively well-controlled cores at low enough entropy. And as usual, we do the preparation for all the slices at the same time. And for detection, we slice out just one of these planes and image this one plane. Since this question will come up probably later, I can tell you straight away. So we did all of these experiments for either of the 2 planes. The results are the same. Okay, so now the first thing that we should talk about is how can we actually detect antiferromagnetic order within the plane without having single site resolution. So you have probably seen these beautiful pictures from the labs of Markus Greiner at Harvard, where he really sees the staggered density ordering for the spins in his lattice that proves the antiferromagnetic correlations. Here we have developed a different strategy to detect this, which takes a detour through momentum space effectively. What we can see with this is we can measure correlations for any k vector, magnetic correlations for any k vector within the first Brillouin zone. So we're not actually limited to observing the checkerboard order, but we can measure any magnetic correlation function there. And this works the following way. So think about the antiferromagnet to begin with, so alternating order of spin ups and spin downs. And then these spins, they have a certain correlation length. So this magnetic correlation decays then with some distance. And now what we do is we apply a pi/2 pulse, which flips all these spins into the horizontal plane. That's still fine, it still stays an antiferromagnet. Then we apply a magnetic field gradient into a specific direction. That is the direction into which we want to measure the correlations. And this magnetic field gradient, these spins start to precess. And if we now choose time and value of the gradient just correctly, what happens is we can wind up the antiferromagnetic pattern such that all these spins essentially point into the same direction after a certain time. So we basically convert this antiferromagnetic order into a ferromagnetic order. And then we apply another pi/2 pulse and flip this back into the Z basis. And with this, we basically convert the magnetic order from an antiferromagnetic order to a ferromagnetic order. And what we then simply measure is the size of the ferromagnetic domains. So for this, we don't need single site resolution to get out the domain sizes. And as I said, I mean, if we now choose a different gradient, so we can either flip this for every other side, or if we choose a different gradient or a different time, we can measure this for any k vector of this spin spiral in the Brillouin zone and also into any direction. And with this, we can then directly measure the magnetic correlations in the plane. So in this case, I show you only the data for the staggered structure factor. So where we measure the correlations on adjacent lattice sites and remove the signs, so get out the staggered structure factor, which measures the antiferromagnetic correlations. And then you see, these are the red data points here. For zero coupling between the layers, they acquire a certain amplitude, which is basically given by the temperature that we still have in the system. And we can confirm that we indeed have correlations, so that this number actually means something by comparing to the local magnetic moment, so just the on-site magnetization, which is just the probability of singly occupied sites essentially, and to the uniform structure factor, that is the structure factor at 0 wave vector. And you see that for 0 intra-layer coupling between the layers, you will see that we have an excess staggered magnetization, and the uniform structure factor is suppressed as compared to the local moment, precisely as you expect. And now, as we allow for more and more hopping between the planes, we see that the staggered structure factor reduces to the local moment. Basically, this means all the antiferromagnetic correlations, they go away, and for strong coupling between the layers, we only have the local moment which governs the magnetic properties of the system in the plane. So the more coupling we allow for between the planes, the weaker the antiferromagnetic correlations in the plane become. So the data that I showed here are the experimental ones, and the bands are numerical calculations using the DQMC Quest code. Now, in the other direction, of course, we would hope to see the opposite. So we would hope to see that these correlations actually build up. And in order to detect this, we use a technique that was pioneered by Tilman Essling and Emanuel Bloch several years ago. And that is basically the idea that if you have the particles in the double well, if you now ramp down the barrier of the double well in an appropriate adiabatic fashion, then you would find out that a singlet state would map onto two particles being in the same vibrational level of the lattice later, whereas the triplet state would map onto two particles in two different vibrational levels of the lattice. And this we can detect spectroscopically, because if two particles are in the same state, they have an interaction shift of U, which we resolve with RF spectroscopy. In the other case, there is nothing. And with this, we can then measure basically the contribution of the singlet state to our original state. And this measures the degree of antiferromagnetic correlations between the layers. And here are the results, and we see that pretty much in the opposite spirit of the previous measurement, that these correlations between the layers, they build up as we increase the coupling strength between the layers. So it's extremely small in the beginning. So when the layers are completely separate, there's no correlations between the layers. Everything is just in plane. And as we allow for more and more tunneling, all these magnetic correlations go into the singlet bonds between the layers, and the intralayer correlations, they disappear. So we can take these two data together and basically compute sort of what is the ratio of these correlations. So on this plot, 0 would mean all the correlations is between the planes along the bonds, and 1 would be all the correlations in the plane. And then you see how this behaves for the different interaction strengths. And if we say, okay, the crossover we define as something like the 50% point, this is somewhat arbitrary as a definition, but sort of as an experimentalist, that what we do just halfway, then we see that this crossover occurs somewhere in the range between 2 and 3 of the ratio between the interlayer coupling and the intralayer hopping matrix element. And it's fairly constant for the interaction range that we are considering. So that's our result here. This result is not too far away, actually, from the predictions of the quantum critical point by Sandvik and Scalapino from 25 years ago. So they considered the large U limit, and they found the quantum critical point at around 1.6. So given the fact that we still have a lot of temperature, that we have the ambiguity of choosing the 50% point here of these correlations and so on, we're somewhere in the ballpark. But I should also stress here that we're not claiming to have seen any quantum criticality here. We just see a crossover between the magnetic orderings in the plane and out of the plane. So the prediction of Sandvik and Scalapino is that this quantum phase transition actually produces a band insulator of singlets, so that these singlets across these bonds, they actually become really a band insulator in this lattice. And the question is, can we actually see any indications of this system being insulating? And we've tried this, despite the fact that we're not precisely at half filling, that we're not precisely at T equals 0. However, we can measure the compressibility still. So we can apply an external gradient and measure how the singlets react to that gradient. And that is shown here on this in this blue data. That is now the measurement of the compressibility of the singlets. And you see that this compressibility reduces as we increase the coupling along the bond. So this could be a first signature that we indeed see that the singlets eventually would become band insulating at low enough temperature. All right, so with this, I come to the end of the presentation. So here is the just the conclusion and the outlook. And let me finally thank all the people who made all of this work possible. So what I showed you here was the PhD thesis of Jeffrey Chan, Marcel Gall, and Nicolas Wurz, who have all graduated or are in the process of graduating just now. And now we have a new team on this setup, and I hope that in the future we will see similarly exciting results. And finally, let me also thank all the funding agencies which have supported us over the past few years to conduct this research. Thank you very much.
Thank you for the wonderful talks. So the floor is now open for questions.
Well, I've got one question. Well, actually more than one, but let's start with one. So this wonderful trick where you turn the antiferromagnetic ordering into ferromagnetic ordering, and then measure that. What I'm wondering is it a unique backward transformation?
Yes, because the antiferromagnetic state does not have a preferred direction. So we could be antiferromagnetically ordered in the X, Y, or Z basis to begin with. And in fact, this is one of the questions that are still there, I think, with Marcus and other experiments, is they always measure in the Z basis, but no one tells you a priori that the antiferromagnetic should always be along the Z direction. And our measurement, we only do a rotation, no matter where we start from. So the antiferromagnetic order could be basically rotated into any direction. We would still only measure the correlations, and that is exact, an exact transformation. Yes.
I see. So you're saying that even if you had antiferromagnetic order to begin with, but you didn't know somehow along which axis it looked antiferromagnetic, you would still see that it had this antiferromagnetic order. By measuring,
we only measure the correlation. We don't detect that directly in which basis the antiferromagnetic is oriented.
Okay, so in a certain sense, you might also say, I mean, that's wonderful, but at the same time, you would say that measuring it this way, you lose the information about what axis it's antiferromagnetic in.
Yeah, but this information usually you don't have.
Yeah. Okay. Right. But well, I mean, if you had single site resolution and you could measure along any axis you wanted, you could get it. But so I mean, we could argue about whether your method is more powerful or less. It's both, depending on what you want to get. But anyway, that answers my question. Thanks. That's good.
So maybe I have one question about the interlayer correlations. So just it looks like fantastic data, but the correlation never really goes above 0.1. If I read the y-axis right.
Here?
Yeah.
Yes.
And so I guess my question is, is that enough to expect to be in this sort of like deeply singlet bound regime? I guess like,
okay, so with these numbers here, you have to be a bit careful. So this graph is not normalized to 1. So perfect singlet would not be 1 on this plot.
Ah, okay.
So these numbers sort of, so we have to make sure that we can actually compare the numbers for the different directions. So these numbers are normalized to the same scale as the staggered correlation function in the plane, so that we actually can compare them to one another.
Okay, thank you.
Can I ask a question?
Yes.
So you mentioned that this system is actually made of many pancakes, like double pancakes, double
Yes.
bilayers, and then you can measure one of these layers or the other one, right? And you're measuring, you're basically averaging over all the first layers, or no, you can actually measure one of the layers of one.
We measure only one layer.
One bilayer.
Yes, we can measure, well, even one layer in the bilayer.
Good.
Yeah.
Okay. I thought that it's just it's like a enhanced measurement of all the first layers, but okay, it's just
no. What we do in practice is, so we prepare the system with many bilayers, and then when the preparation has come to an end, we freeze the distribution by quickly ramping up the lattices. Then we apply a very strong vertical magnetic field gradient, and then do basically tomography to slice out one layer of the optical lattice. Then we apply some state manipulations, which brings only those atoms into the state that we detect.
And then on this layer, you don't have, in the plane, you don't have spatial resolution, correct?
Exactly.
Yes. Okay. That's very cool data.
Now, Michael, if I've understood correctly, in this, going back to the single layer results, you see, as you change, say, U over T in the usual way, you see a crossover between the metallic behavior and the Mott insulator behavior. Now, if this were a Bose gas, certainly at zero temperature, it's a sharp phase transition. At non-zero temperature, maybe it's a little bit soft because you have that quantum critical region, but it still sort of looks like a phase transition. So why is there a difference? Why is it a crossover for fermions and a phase transition for bosons?
Okay. So you're referring to this picture?
Yeah, that's
That is because there is this second order phase transition below.
So that the antiferromagnetic regime just basically prevents you from seeing the kinds of things you might see with the bosonic one, because
think about it this way. So the metal to Mott insulator crossover is actually not the real deal, because it's very simple to see that the Mott insulator cannot be the ground state because it has a huge amount of degeneracy, right? You could basically exchange a lot of these spins and nothing would change to the total picture. So this is not a unique ground state, but it is an excited state. And the uniqueness of the ground state only comes when you properly take into account that there is the super exchange mechanism. And then you have one ground state, which is the antiferromagnetic one. And indeed, it is antiferromagnetic for any interaction larger than 0. So as you see here on this plot, sort of the TC exponentially goes to 0 as the interaction goes away, but you still have this then itinerant antiferromagnetic ground state. So the ground state does not fundamentally change its property with interactions, and that is very different from the bosonic case. Right? For the bosonic case, the ground state is superfluid for weak interactions and strongly interacting for Mott insulator for strong interactions, and then there is the quantum critical point in between. Here, the ground state is always antiferromagnetic at half fillin.
And the antiferromagnetic state is also insulating, of course.
Yes, but not that much.
So tell me about that.
So in order for the super exchange mechanism to work, you need a certain amount of fluctuations in the system. So you can think about it in the following picture. So how does a particle on one side know whether the neighboring side has the same spin or not?
Sure.
Right. So the process it goes there in a virtual hopping process, and then it goes back.
Right.
And if the neighboring side has an opposite spin, it only costs an interaction energy of u. And if it would have the same spin, it would have to go to the next Bloch band. And that's why that the neighboring state has an opposite spin is energetically preferred. But for this, we need fluctuations, right? If we would have 0 fluctuations in the density, we could never probe that effectively.
Right. Now, my recollection is that in the Bose case, you also have that regime of some fluctuations as you change U over T. The phase transition happens, but the fluctuations don't completely disappear until you increase the interactions. But it's still an insulator.
Yeah, so to give you a feeling for that is if you look at the peak of the antiferromagnet here, which occurs at around, say, U over T on the order of 10. Yeah. The amount of double occupancies that you have in this system is on the order of 5%. Still. So this means it is a pretty good insulator, but it's it's far from a perfect band insulator.
Mm-hmm.
At 0 temperature. That's sort of that's what theory tells us.
Yeah. Well, I'm just trying to make that but
it's true that these fluctuations go away the higher you bring up the interaction energy. But then also your TC goes down quite a bit.
Yeah. Yeah. But of course, it seems like it's not, well, maybe getting too much into the weeds here, but having fluctuations and having conductivity aren't exactly the same thing.
Yes. Okay.
And so what I'm wondering is, maybe it's a matter of defining what we mean by an insulator.
Yes. Okay. Fine.
Because I'm just again remembering the bosonic Mott insulator. It has a sharp transition, but the fluctuations haven't completely gone away. But the thing that does go away, I think, is the conductivity. But I'm having a hard time remembering now.
So it's the superfluidity which goes away in the bosonic case, right?
Yeah. Okay.
The superfluid order parameter disappears.
Right.
But
which, of course, is not the same thing as saying that the conductivity disappears.
Yes.
Because usually when people say that the superfluidity disappears, what they really mean is the coherence disappears.
Yeah, maybe yes.
But anyway, I think now it's getting too detailed.
But here, I mean, let me just iterate this.
Getting concerned.
Here we have fundamentally the same ground state for any value of u. So it's always an antiferromagnetic order ground state. It changes its character as we go from weak U to large U.
Yeah.
But it's still fundamentally dominated by the antiferromagnetic correlations, and
right.
there is
always
no change.
And that's always a sharp transition, the way you've shown it in this diagram.
Excuse me?
It's always a sharp transition to go into the antiferromagnetic state.
Well, that's a second order phase transition.
Yeah. Right. Right. But it's sharp.
In 3 dimensions, I should say. Yes.
Yeah. Okay.